Now let's go to section 3 of this notebook, Rules of Probability 1, Addition Rules. This time we're going to take a little bit more theoretically perfect point of view and begin with definition of probability. Here we go. Let S be a non-empty set, which we call the sample space, and any subset of the set S will be called an event. A set function P is called the probability on S if it satisfies, well, these conditions. Number 1, any probability is between 0 and 1. We discussed this before. The probability of an empty event is 0. The probability of entire sample space is 1. Again, the same as what we discussed before. This is somewhat new. The probability of the union of mutually exclusive events A1, A2, A3, and so on is the same as the sum of their probabilities. And this is a little bit new and of course a little bit harder because we have infinite sum here. Compared with the previous situation we talked about before, where we had just 2 mutually exclusive events, this is certainly a step up. However, this kind of consideration is necessary, particularly when we have infinite sample space. Let's discuss these properties in a little bit more detail using some graphical explanations. Here we go. We studied this picture before. The probability of the union, mutually exclusive union, is the sum of their probabilities. Well, as you can see, we don't have any overlaps, so we can simply add up these two in terms of area if you want to. Next, what if there is an overlap? Well, one way to view it is the following. The probability of A other than B, A except for B, which is this blue crescent region, and the probability of B except for A, which is this red crescent region, B not A not B. And finally, plus the intersection, probability of A and B. And this decomposition gives us a sum of 3 mutually exclusive events. As you can see, there's no overlap between those three, excuse me. So we can add them up. Another way to view the same thing is this way, of course. But here we go. What is probability of A? That's probability of A not B, which is this blue crescent region, plus the intersection probability of A and B, this purple region. What is probability of B? That's probability of B not A, where my mouse is right now, this red crescent, plus the intersection probability of the purple region here. So if I add these two up, the purple region, the intersection is counted twice. That's why I have to subtract it away so that we have the fair comparison. Either you can use one way or the other. Personally, I prefer this one. Just decompose everything and add them all up. Or just go with something like this, even if we have a lot more sums. The final picture, this one shows complement events. A and A complement add up to the full sample space 1. So if you subtract this PA away from total 1, we get the final formula, which is quite useful, calculating the probability of the complement event, which is here. The other rules are pretty much straightforward. Inequality rule here. If B includes A, as you can see, then probability of B should be bigger. Duh. And this one is a little bit harder to see, but here we go. Probability of intersection is in general less than or equal to probability of sums, as you can see in this picture, because there are overlaps that may be counted twice, thrice, 4 times, and so on and so forth. The union usually is less than the probability of the union is less than the sum of the probability usually. Of course, if they're all mutually exclusive, then they have to be the same. Something further, now that we are discussing Venn diagram, we have to consider some logic. And here we go. A or B corresponds to the union. A or B. A and B corresponds to the intersection. Remember this? Not A corresponds to the complement. Okay, are you ready? Here's an example. This time let's do this with 3 sets. A, B, C. Okay, we have this Venn diagram. What is A or B or C? A or B or C? Or, that's union, isn't it? So union them all. You have to shade them all. How about A and B and C? Intersection of everything, you have only the middle part. Here comes a little bit difficult one. A and B or C versus A and B or C. Where is the comma? Where this comma plays a humongously important role here. A and B first or C, or A and B or C. Well, here we go. A and B first, which gives us this brown region with black boundary, or C, which is blue region, and then shade everything together. How about the other? A and B or C. B or C first, so we get the union of B, C, so we get actually entire circle B and circle C, and A, so we have to consider among those circle B, circle C, we have to get the region inside A only, shaded kind of like this. Compare that with the previous picture. A and B or C versus A and B or C. There's a significant difference. I'm going to leave the final 2 problems to you guys. They're not going to be that simple. Again, commas play significant roles. Oh, also, how do you deal with but? Well, think about those. Now let's go over to a little bit more concrete example here, and this kind of problem is rather realistic. Here we go. An insurance company examined its customer base. It finds 36.7% of the clients purchased an auto insurance, A. 41.2% purchased homeowners insurance, H. 22.9% bought a life insurance policy. Furthermore, 21.3% got both homeowners and both auto and homeowners, 14.1% got life and homeowners insurance, and 8.5% got auto insurance and life insurance. Finally, 7.2% purchased all 3 types of policies. Wow, how do we handle that? Well, before answering these questions A, B, C, and D, it is absolutely necessary that you get right numbers. If you have right numbers at each region, then you can use addition rule to answer A, B, C, and D with appropriate shading. If you do not get right numbers, no matter what shading you get, you're going to get a wrong answer. And let me show you a wrong answer first. And let me get that down here. This is wrong, by the way. So 36.7% of the client purchased auto insurance, so 36% here. 41.2% purchase homeowners insurance, so 41.2% here. 22.9% bought life insurance, so that goes over here. 21.3% got both auto and home, so goes here, and so on and so forth. We have all these numbers, but if you add up all those numbers, that number will exceed 100%. If you see that, at least you earn a little bit of credit. A little bit, I said. But if you just still didn't see it and do the computation from here, that's just zero credit no matter what you do. Just doesn't make any sense. Now, I claim, out of all these numbers, there's one number that is correct. Everything else is wrong. Which number is correct number here? The correct number is right in the middle, 7.2%. This one is correct. Everything else is wrong. And how do we correct it? Well, let's go to this correct solution and discuss that. Okay, 7.2%, right in the middle. There's no chance for exclusion, so that's right. And then let's see, let's backtrace. 8.5% got auto insurance and life insurance policies together, auto and life. And they add up to these two regions where I'm moving my mouse around. Intersection between A and L. And that adds up to 8.5%. Here we have 7.2%. So what we have left here, we have to do this kind of computation. 8.5 minus 7.2. And we end up with 1.3. Oh, where did that picture go? Sorry about that. That's how you get 1.3% there. How about the next one? Keep backtracing. 14.1% got life and homeowners insurance. So life and homeowner, here where my mouse is running around. Out of that 14.1, 7.2 already have all three. So what's the other? So 14.1 minus 7.2, we end up with 6.9. That's how we get 6.9% here. Keep backtracing, we have 21.3% minus 7.2. That's how we get 14.1% here. Keep backtracing, we get 22.9% bought life insurance policy, right? Okay, 22.9. And we have to subtract away the middle, and then here auto and life but not all three, and here auto and home but not all three, all those together. And that turns out to be 7.5%. How do you get this 13.0%? Well, I hope you can do that. 41.2% purchase homeowners insurance. Out of those, you have to exclude 14.1, 7.2, and 6.9. Those away, and then you get 13.0%. This one was obtained pretty much the same way. Oh, I spent a lot of time explaining the Venn diagram, so I don't know whether I'm going to have enough time answering these questions. If you select a customer at random, what's the probability that selected customer has an auto insurance and homeowners insurance but no life insurance policy? Auto and home but no life insurance. Auto and home, so it should be where my mouse is. Auto and home. But no life, so outside L, we have this 14.1. As a matter of fact, well, here we go. Let's answer second question, and I'll leave the rest of the problem to you. If you select a customer at random, what's the probability the selected customer has auto or home but no life insurance. Auto or home, but no life, but so outside L, we have something like this.